Okay, so here it says if the B field increase at a steady rate at a constant induced current appears in the coupling of radius r. Okay, so here we assume within this yellow area we have some uniform B field. Okay, indicated by the green cross. Okay, so means the B field is actually pointing into the page. Okay, so and it is uniform over the area. Okay, but it is increasing with respect to the time. Okay, 就是在时间上它是在在增加的。Okay, the B field increases at a steady rate， 就是以一个等的速率在增长，或者是线性在增长。Okay，and induced electric field exists even when the ring is removed。Okay， 那我们就也不需要有一个实体的环存在啊。前面有讲过一个 eddy current 的概念。The compute picture of the induced electric field displays as a field line. Okay, so actually, suppose this is a closed loop. Okay, this is a closed loop that we would like to consider for applying the Faraday's law. Okay, so for the Faraday's law, it is something like this. E dot ds equals negative d phi b dt, something like this. Okay, so yeah, of course for this line integral you need to define a path for it to integrate. So suppose it is like this, and in that case if the B field is increasing, the E field generate by this B field changing will be like this. Okay, this is like this is the generate E field. This is a generate E field. Okay, so this generate the E field generate, and actually this E field is counterclockwise. So actually, according to Lenz's law, you can easily know why it would be like that. Yeah, because originally the B field is pointing into the page, it is increasing. So according to Lenz's law, the generated B field should be pointing out of the page to offset this change. So in this way, the B generated by this loop should be like pointing upward. Okay. So the B field should be the B induced should be pointing upward. So in such a way, if B induced is pointing upward, using the right hand rule, your thumb is pointing out of the page. Your four fingers will be like counterclockwise. So it is like this. So if there's a current flowing like counterclockwise, so this loop will generate B induced pointing out of the page. Yeah, or maybe, yeah. Okay, so okay, so here in D it says 4 similar closed paths that enclose identical area. Equal EMF are induced around path 1 and 2. Okay, so it is actually mentioning mentioning this red path. Okay, so this is path 1, path 2, path 3, and path 4. Okay, indicated by this green path. So actually it says path 1 and path 2 have the same area, and the B field is uniform over this region. So it tells you that the EMF for path 1 and path 2 should be the same. Yeah, but path 3 only. For path 3 actually this one and these two also have the same area, but part of this area enclosed by this path is out of this region. Okay, so which means that this So this part doesn't contribute to the phi b. Okay, no contribution to the phi b. Okay, I mean no contribution，它不会贡献到这个 phi b，no contribution to phi b. Okay, for this part. Okay, so which means that this thing will be smaller. Okay, this thing will be smaller. This phi b will be smaller. Also, the d phi b dt will also be smaller. So, which means the EMF generate along this path 3 will be smaller. Okay, so here it says a smaller EMF is induced around path 3, which only partially lies in that region. So no net EMF is induced around path 4. Okay, because this path 4 is all the way out of the yellow region. Okay, so no EMF is actually across over going through this path 4. Okay, so so here let's take a look at this sample problem. So it says in the figure takes R to be this length and then dB dt is this value. Find the expression for the magnitude E of the induced E field at point within the magnetic the B field, okay, at radius small r from the center of the B field. Evaluate the expression for R equals 5.2. Okay, so here let's consider R is a variable first, and then we get a general expression, and then finally we plug in R it to be 5.2 centimeter at the end. Okay, so integration of E dot ds. Okay, so of course this is the left hand side of the Faraday's law. And then here we also assume that, okay, so suppose this is a circle with a center which is the same as the center of this region. Okay, so in that case it will generate E field. Okay, so the E field will be like parallel to the ds. Okay, so suppose that ds will be like this at this point, and maybe ds will be like that at that point. Okay, so we will assume okay, so the path is like counterclockwise. The path is like counterclockwise. Yeah, because we can easily find that. Okay, so the B field is pointing into the page and dB dt is a positive value. So yeah, so the B induced will be pointing off the page, and in that case, this loop should be counterclockwise, and the loop of this E field should be counterclockwise. Okay, so we can also assume that E and ds always point to the same direction. So E dot ds is the same as E times ds. And E will be uniform, okay, over the same radius. Okay, so we can put E outside, so it is nothing but the length of the circle. So it is nothing but E times 2 pi r. This is actually the same as what we did in chapter 29 for the integration of B dot ds. And then phi b will be B times A, okay. So originally should be the surface integral for the B field, okay, enclosed by the loop, okay. But B field is uniform and also pointing to the same direction as dA, so it turns out to be a multiplication. Okay, so the area is nothing but the area of a circle, pi r squared. And then we take the derivative, with respect to time. So it turns out to be pi r squared is independent of the time. Okay, so finally it becomes a dB dt, dB dt. Okay, so we will like to make use of this value, putting it here. Okay, so so here is nothing but 0.13 pi r square, 0.13 pi r square. Okay, so so for the Faraday's law, it will be integration of E dot ds equals negative d phi b dt. Okay, so on the left side is E times 2 pi r, and then on the right side is this one, negative 0.13 pi r square. Okay, so we can make some cancellation. Pi and pi can be cancelled. R and this R can be cancelled. So finally, E will be negative 0.13 over 2, 0.13 over 2, 0.13 over 2, and then R. Okay, only R remains. Okay, so here if we would like to know the magnitude, okay, the magnitude, find the magnitude, okay, find the magnitude, which means we take the absolute value should be 0.13 over 2R V over M, okay. So the SI unit for the E field will be V over M or N over C. Okay, and finally, we would like to evaluate the expression for R equals 5.2 centimeter. So E for R equals 5.2 centimeter will be 0.13 over 2 times 0.052, okay, so which is nothing but 3.4 millivolt per meter. Okay. Okay, so here we would just like to find the induced E field inside this region. So the next part of this question is here we would like to evaluate, find the expression for E field that are outside the B field, and evaluate the expression for R equals 12.5 centimeter. And here the radius is only 8.5 centimeter. So in this case, d phi b dt, okay, d phi b dt will be 0.13 pi capital R square. So here actually, we would not take this path for this question. Actually, we will take a path that is outside. So this will be the closed loop, okay, that we will apply the Faraday's law. But actually for the dB, the phi b or d phi b dt, okay, only this part have the B field or the B field changing. So in that case, we would not count the full R, okay, full small R, okay, because for the outside part we don't have any B field or B field changes. So the phi b is up to the whole region here. So we would count up to capital R only. So here for the Faraday's law, integration of E dot ds equals negative d phi b dt. Okay, on the left side it is actually the same, E times 2 pi small r. Okay, nothing changed. So because this one is only related to this path, okay, so we still count up to the small r. But for the right hand side, it is negative 0.13 pi capital R squared. So in such a way, So yeah, we can directly take the absolute value of E, yeah, because we just need to ignore this negative sign. So it is nothing but 0.13 over 2 small r and then times capital R squared. Okay, so this is the expression for the induced E field that is outside the B field region. Okay, so here we try to evaluate at R equals 12.5 centimeter. So this is nothing but 0.13 over 2 times 0.125 and then times 0.085 squared. Okay. Okay, so this is nothing but 3.8 millivolt per meter. Millivolt per meter. 3.8 millivolt per meter. Okay, actually this value is still a little bit larger than this one because the E field actually increase linearly. Okay, this one is actually increased linearly. Okay, so which I mean is this E field is actually proportional to R. So it will be increase all the way up to here. And then actually outside, okay, so all these are the constants. So for the outside part, the E field is inversely proportional to R. So actually it will be something like this, okay, increase linearly, and then finally is yeah, so this is increase linearly, and then finally inversely proportional to the R for the outside part. Okay, so this one I think it is not so difficult because yeah, we have some seamless calculation before where we are considering the Ampere's law. Okay, so here is like we try to exchange B field and E field. Yeah, of course the mechanism are not the same, but yeah. So for the Ampere's law, is like something generate the B field. Okay, the something is the current. The current will generate B field, but here is changing B field will generate induced E field. Okay, so here we like to introduce the third circuit element, linear circuit element, yeah, in the circuit theory. So this is actually the inductors, 就是电感所以我们已经学了3个电路元件的电阻、电容、电感resistor、capacitor and inductors。OK， 那 inductance 就是那个电感值虽然这本书很奇怪，他们这本书没有 resistor、capacitor、inductor， 它都叫 inductance、resistance、capacitance 但是电路的话，我们会分开来，就是 tance 或者什么 inductance、resistance、capacitance 那些叫做电阻值、电感值、电容值，就是那个值本身那个什么 inductor、capacitor、resistor 就是那个元件本身是不太一样，它好像都混合起来。Okay, so here is the definition. An inductor is a device that can be used to produce a known B field in a specific region. If a current I is established through each of the n windings of an inductor， 就是 n 个圈，就是把导线绕成一 一个圈，就是其实你可以想象成上一章学的那个 solenoid 其实是一样的。OK，so 但是当然不一定是那个形状，但是通常我们都想象成那个形状，对。OK，a magnetic flux phi b links those windings, and then the inductance L of the inductor is L should be like this. Okay, so this is the definition. This is the definition of the inductance. Just as for the capacitor, the definition is C equals Q over V. This is the definition for the capacitor, and this is the definition for the inductor. Okay, so actually the capital N refers to the total number of turns. Okay, just as what I mentioned, the total number of turns. Okay, N windings, actually the total number of turns. And then the phi B is the magnetic flux generated by this inductor, and then normalized by the current. Okay, which means it is proportional to the number of turns. Okay, proportional to the number of turns. Also, after the number of turns is fixed. Okay, so the only changing thing is if you provide a larger current, it will also generate a larger magnetic flux. Okay, so these phi b and I will have a fixed ratio, and then if you all multiply this ratio multiplied by the n will be the inductance. So if you would like to increase the inductance, so usually we would like to have more turns. Okay, so here the SI unit for the inductance is Henry, H. Okay, so a quick summary is for the resistance, the SI unit is ohm. Okay, for the capacitance, do you still remember the SI unit is farad, F. Okay, for the inductor, the SI unit is Henry, H. So don't be so confused. don't confuse yourself. Actually, so this is the capacitance, but C is also a SI unit for the charge. Okay, so maybe when you need to study, you will still a little bit confused. Yeah, but actually. Yeah, memorizing the SI unit is important. Okay, so on the bottom right part, this is an interesting story. Okay, so here it says the crude inductor with which microfarads discovered the law of the induction. Okay, 所以这个是说他发现这个电感时候的这个最原始的那个电感装置这个在什么皇家博物馆里面。So in those days, LT such as insulated wire were not commercially available. 他说当时就是这种有这个绝缘那个包着这个导线，它不是很能买得到因为怎么说，就是你有一根导线没问题，你有那个金属，你就可以把它压成一条线，但是你要绕成一个线圈的话，那你不能够绕两个圈之间互相碰到，所以你一定要在线的外面有一个绝缘层，那你才能绕得起来。OK， 所以it is said that Faraday insulated his wire by wrapping them with strips cut from one of his wife's petticoats 所以他是说他把他老婆的其中一件衣服把它剪下来，然后去绕这个线所以现在应该是不能想象了，就是怎么可能去碰老婆的衣服呢Okay, so Okay, so here is actually derive some formulas. So considering long solenoid of cross section area A, the flux linkage there is n phi b. Okay, so n phi b is nothing but this one. Okay, so the flux linkage will be n times L. Okay, so this is what I mentioned for several times. The small n means the turn per unit length. The turn per unit length. Okay, so which means this n, this capital N is n times small l. N times small l. So the number of turns per unit length times the length of this solenoid. Okay, so n times L will be the capital N, and then phi B will be B times A. So nothing special. The magnetic flux will be the B field. Okay, we assume the B field is uniform inside the solenoid. So B times A will be the phi B. And then also in chapter 29, we also derive a formula as B field inside the solenoid will be mu0 times In. Mu0 times In. Okay, so in this case, okay, so making use of the definition in the previous page, L will be n phi b over I. Okay, and then we plug in n phi b to be this thing here, okay, over I. And then we also plug in b to be mu0 In to here. So n times L here, and then b will be mu0 In, and then times A over I. So finally we can actually cancel this I and this I. Okay, so this is nothing to do with the I. And then we also move this L to the left side. So which on the left side we have a capital L over L, which means the inductance per unit length. The inductance per unit length will be mu0 is a constant, 4 pi times 10 to the -7. And then here we have n square. L already go to the left side, mu0 is over here, A goes to here. Okay, so this is it. Okay, so mu0 is constant, n square is the inductance per unit length. Okay, so if we would like to increase this value, we would like to make a more compact windings 就是要那些线圈绕得更紧密，它才能够在单位长度里面绕得更长。OK， 那如果你没有办法做到这个事情的话，那你就要增加那个面积，就是绕一个更大的圈。OK，so so the last choice to increase this L over L, this capital L over small l, will be like to increase the cross section area. Okay, which means you make the cross section area bigger. Okay, so this phenomenon we call it the self-induction. So in Chinese we call it 自感应。self-induction. Okay, so here it says if two coils which we can now call inductors, are near each other, a current I in one of the coil produce magnetic flux phi b through the second coil. OK， 所以他这里在说的事情是这样的So suppose we have a circuit like this. Okay, so first we have a battery. And then we have a tunable resistor. Okay, we call it a tunable resistor. 可变电阻的意思是本来电阻就这样嘛，那直接接触去不就好了吗？那这里有一个 tip， 有一个接触点 那我接触到中间的话，那我就是电流的话就只到这里就出去了哦，右手边就不管了。那如果我的接触点在这里的话，那我就取完整个电阻啊。如果我取到这里的话，那我就接近取不到任何的电阻。那我就是透过调整这个 tip 的位置，去让这个电阻值可调啊，可以调的，用手去调的。通常都会有一个旋钮这样去转啊。OK， 所以so for this tunable resistor, it is just like to adjust the current going through. Okay, so which means this is the R, and then maybe there will be some small R over the whole loop. Okay, so suppose if we can change this resistance, okay, we will be able to define the current for this loop. Okay, so 可以透过改变这个电阻值来决定这个线圈的电流。所以有电流之后啊，那这里是一个 solenoid 嘛，所以它有很多圈。那现在我们只考虑2圈啊。So first we would like to consider maybe for the first loop. So the loop here, okay, so the loop here, okay, so of course the current is flowing from the top, okay, like this, okay, like this. So for this loop itself, it will generate B field. It will generate B field pointing downward, okay, pointing downward. Okay, so in such a way, this B field will go through the other loop, the second loop or the other loop. So in such a way, this B field, originally there's no B field, and now you give it a current, and then it suddenly generates a B field. So in such a way, the second coil will follow the Faraday's law, okay, because your B field, the magnetic flux for the second coil is increasing. So in such a way, it will generate a B induced for the second coil pointing upward. Okay, so to offset this change. So this is actually called the self-induction. Okay, 所以就是自感应就是这样，就是这个整个是一个电感，但是你单独看一圈圈看的话，就是一圈它会产生 B field， 那它产生的 B field 在另外一圈看起来就是你征兆我的磁通量，那我就要产生一个反向的去抵抗你，这样就是这样，所以它就是自感应。Okay, so we have seen that if we change this flux by changing the current, and induced EMF appear in the second coil according to the Faraday's law. So the induced EMF appears in the first coil as well. So this process is called self-induction, and EMF that appear is called self-induced EMF. Okay, 所以它会产生一个 okay. So according to this B induced, according to right-hand rule. Okay, so it will have the EMF to be like the opposite direction to the current, to the original current. Okay, so this process is called the self-induction, and the EMF that appears is called the self-induced EMF. So it obeys Faraday's law of the induction just as the other induced EMF do. Okay. So here we would like to quantify this self-induction. So for any inductor, okay, we would like to consider n times phi b as the flux linkage. Yeah, actually the numerator part of the inductor. So so if you still remember, the definition is L equals n phi b over I. So here we just move this I to the left side and then swapping left and right. So n phi b will be L times I. Okay, so according to the Faraday's law, okay, we can have EL to be d phi dt, origin d phi dt, but if we have multiple terms, we just multiply n there. Okay, so n phi b will be L times I, so it is nothing but negative dli dt, and then L will be a constant, so we just put L out of the derivative. So EL will be equals negative L di dt. Okay, so this is a formula for the physicians, but in circuit theory, I never use this expression. I always use V equals L di dt. Okay, L di dt. So which means that it is somehow like the EMF is in the opposite direction of V. Okay, so because for circuit theory we always use V and I for everything inside the circuit. Okay, we don't try to introduce our EMF. Sometimes you EMF, sometimes you V, and then you will be confused. Okay, so the idea is like actually I honestly I only use this one. I never use this. So here it actually is that an induced EMF EL appears in any coil in which the current is changing. So how do we apply this? Okay, so here is like this is the original battery, okay, or the external EMF, okay. So this is a fix, okay, and then here will be a resistor. So for this V, maybe I say this is VL, okay. So this VL will be like this, okay. So VL will be related to this current going through, okay. So di dt, okay, we just take the positive value, okay. So yeah, in that case you will have less probability to make mistakes, because these two are equivalent, but I think you do plenty of mathematics. Yeah, so sometimes if you have many negative signs, so during the computation, or you have many negative signs, then you will have more possibility to make mistakes. So yeah, so that's why or in the circuit theory, we usually use the V equals L di dt rather than the EMF with a negative sign. So in such a way, this one we have all the way positive sign, then yeah, it will be easier to handle. Okay, so I think something I have mentioned before, but I would like to recall it again. So actually for R, C, and L, okay, so for R, C, and L, okay, so let's say this is VR, and then this is the current I, okay, so we will have VR equals I times R, okay, so this is actually the Ohm's law. Oh, actually we learned it in chapter 26. Chapter 26. Okay, so for capacitor, yeah, we also have the current like this. Suppose this is a VC. Okay, so we always define the direction like this. Okay, this is positive, this is negative, and then the current should be from the positive side to the negative side. Okay, so in such a way we have I maybe I put it I out here, so that you don't confuse. IC equals C, this is a capacitor C dVc dt. IC equals C dVc dt. Okay. So how does this come from? This is actually comes from Q equals CV. Okay, and then you take the derivative on both sides, so dQ dt, and then C. So you take the derivative of this side, C will be a constant, so we have a C dV dt, and dQ dt will be I. So this is y, this equation like this. And for the inductor, okay, so here VL, okay, so all the positive and negative side and all the current direction will be the same. Okay, so don't you need to remember a lot of version. Okay, so if you use the EMF here and then it tends to be another direction and then you will be confused. So this will be VL equals LdIL dt. Okay, so we will make use of these three in chapter 31. Yeah, to solve for the actually you can use these and then with the KCL, KVL to write out some differential equation, to write out some linear constant coefficient differential equation, and then we will just solve the response for the circuit. 就是可以我们解一些实践的一个，我们中文叫做时间的响应时间的响应就是一个 time domain 的 waveform 出来，透过解一些 wave 方程。Okay, so this is so something I could also mention is that for capacitor, the voltage is continuous. V is continuous. Continuous. 就是 for C, okay, I is not continuous for C. 就是中文的意思就是对于一个电容来说，这个电压差的话是连续的，但是电流不一定连续，电压会连续其实你不用记很多的话，它在这个微分符号里面，它就要连续，它不连续的话，它一低的话，它就变成无穷大所以很简单的，不需要记太多，你只要知道有这个式子就好。类似的I is continuous I is continuous for L 就是电感的话，就是电流连续，但是电压不连续就是它们两个是相反的，所以要记住这个东西，因为对。Okay, so for this part we will just skip it for now. Okay, we will come back maybe next week. Okay, we will try to revisit this part again. Because so far I don't know how to let you know why this expression will be valid. Wow, how come there will be an exponential function? You need to know how to solve a differential equation. So after finishing this chapter, I will let you know how to solve the constant coefficient ODE, okay? And then you know why it will be like that. We can actually write a simple differential equation. Okay, so it will be something like this: E equals R times I, and then plus L di dt. Okay, something like this. Okay, so actually based on this circuit, we can write this differential equation, and then by solving this equation, we can get this solution. Okay, but so far I don't know how to tell you why it be like that. So so let's skip it for this moment. We'll come back later. Okay, so maybe let's have a